So let's just get going. This is welcome everyone to the November LBNL Quantum Information Science Colloquium. It is a pleasure to have Dr. Nicolas Roch. He's going to talk about Josephson metamaterials, a new platform for quantum optics. Nicolas is a permanent researcher at CNRS Snail Institute. He obtained his doctorate from the University of Grenoble in 2010 and then worked at École Normale Supérieure under Professors Huer and Devoret from 2010 to 2012. And he also spent 2012 to 2013 here in Irfan's research group as a postdoc. And he was among the first to build, design, and operate quantum limited Josephson amplifiers, and his main research nowadays consists on quantum simulation for circuit QED, quantum limited parametric amplifiers, Josephson junction metamaterials for high impedance quantum circuits, and QND measurements in quantum mechanics. With all that, I just leave you with Nicolas. Take it away, Nicolas.
Thank you, David, for the introduction. So let me share my screen. Okay. Do you see my screen properly, full screen? Yeah.
Yes.
Great. Okay. So thanks again, David, for the introduction. Good afternoon, everyone. Good night if there are French people around. So it's a great pleasure to be with you all today. It's actually a great honor, I should say, to be invited to this colloquium. As David said, I now work in Grenoble, France, in the French Alps, and I am part of the Quanteca team, a team which aims at building superconducting quantum devices, qubit, quantum limited amplifiers. But today I will speak about such devices. By the way, do you see my pointer?
Yes, we can see the mouse.
Okay, thank you. And I will discuss this type of devices. So you have a chip, it's silicon-based. You barely see it here, but we have a Josephson metamaterial. And by probing it in transmission, so it means that we can send some signal from the left and take it out from the right on this picture. And using this kind of metamaterial, Josephson metamaterial, we can have a lot of fun with quantum optics experiments. But before I dive into science and physics, let me introduce our team in Grenoble. It's a team of 15, 20 people. I would like to mention my colleagues, Olivier, Wiebke, and Cécile, who are also a CNRS researcher. But more importantly, I would like to thank and highlight the contribution of Giulio, Martina, Arpit, Luca, and Anuj, who are PhD students and postdocs who mainly contributed to the work I will discuss today. So a big thanks to them. Also, I would like to thank our various collaborators in France and abroad who helped us for various aspects of this project, ranging from theory to device production or calibration issues. Okay, so this is the outline of my talk. I divided it in 3 parts. First, I will start with an introduction about traveling wave parametric amplifiers. Such devices were invented by Irfan, I would say 6-7 years ago now, but still, since it's a colloquium, I wanted to give you the basics. So I'm sorry for the specialists in the audience, but I thought it was important to go really step by step today. Sorry, give me a sec. Then I will discuss a very specific issue that 2 paths are facing, which is called the phase matching issue. And last, I will discuss a very recent experiment quantum optics experiment we've done with the 2-power. We observed for the first time vacuum to mode squeezing, so I would try to walk you through that. I see a question in the chat. Yes, David is right. Feel free to interrupt me with question, of course. Okay, now I see the. Okay, sorry. Okay, so driving wave parametric amplifiers introduction. Let's start with that. So this is this kind of scheme is the standard one that you might want to use as an experimentalist to probe a system. In this case, I depicted the quantum system, but it can be any system. So if you want to infer some state of the system or some information of the system, you want to send a probe in, it will interact with your quantum system and comes out, and you want to measure this outcoming probe. It sounds very easy, like that, when said like that, but actually it's not. There are several complications, and the first one is that your quantum system has very low energy. It's very fragile. So the probe has to be extremely weak. And in most cases, we speak about signal of few photons. So measuring few photons, especially few microwave photons, accurately and with very high sensitivity is extremely difficult because we speak about very, very tiny energies. So to make a long story short, you need high amplification to boost the signal, so you can measure it with your favorite oscilloscope or your favorite digitizer. But at the same time, you also want this process to be low noise, because if you amplify your tiny signal, but you add so much noise that it buries everything out, basically you don't win anything. So these are the two requirements. Now you might wonder what kind of applications for such amplifiers. The two obvious ones are superconducting qubits or spin qubits. In the context of quantum information, I think there are many people who are aware of that. Things that you might know less, or which are maybe less known from this community, is the search for dark matter. I know that also Irfan has project in this direction, but also I wanted to really say that this is a growing field. There are more and more demand. This community of dark matter detection is really looking in our direction because they want to learn this extremely low noise techniques. Also, you can think about quantum limited electron spin resonance. ESR is everywhere, from material science to medicines or pharmaceutical application. So if you can boost ESR and detect an even smaller and smaller amount of spins, you can also have very, very large applications. And one last application that I like a lot is astrophysics detector. Here, what you see is actually a camera. So now, these days, astronomers, they are using arrays of microwave resonators, of superconducting microwave resonators, as many pixels of a camera, and they can image the sky, image what's coming from the galaxies, thanks to these kits, like for kinetic neutron detectors, cameras. And since they are microwave resonators, since each pixel is a microwave resonator, if you can have a very good microwave amplifiers, it will also benefit a lot to them. So these are, of course, not all the applications. It's just a short snapshot of what you can do with this quantum limited amplifier. Okay, so now let me introduce a very important concept. We spoke about gain, we spoke about noise. Now, what about quantum mechanics? What does happen? And to understand that, I like this sentence from Carlton Caves. Let me read it. And Carlton Caves said that the last essential quantum mechanical stage of a measuring apparatus is a high gain amplifier. It produces an output that we can lay our grubby classical hands on. So this sentence, I think, is very, very deep. It states clearly that if you want to get the best of your amplifier to measure a quantum system, you also need to understand it from a quantum mechanical point of view. And you cannot just treat this amplifier as a simple classical one. And if you do the proper treatment, as done by Cave in this paper, you can see that there is actually what is called a standard quantum limit to amplification, which means that this noise, this thing you are trying to reduce as much as possible, as a limit. And you cannot reduce this noise below this limit, which is called the standard quantum limit, and which is equal to h bar omega, so omega being the frequency you want to measure, divided by 2 kb. And it's basically vacuum fluctuations, or Heisenberg principle, if you want, translated to amplification. This h bar omega by 2 is actually the one you find in Heisenberg inequality. So this is about the standard quantum limit. Now the question is how to get a detection chain, a full detection chain that is entirely quantum limited. So since I am an experimentalist, I like to see an example of fridge, more specifically of one of my fridge, and you see that this is so you have various stages. 100 Kelvin, 20 Kelvin, 4 Kelvin, 700 millikelvin, 20 millikelvin. And at the coldest stage, which is up there, this is where, for example, you have your qubits, right? So now the question is how to measure this qubit with a fully quantum limited chain. Not only the first amplifier, but all the chain. So from this point up to the output there, where you will put your oscilloscope. And the trick is to have several amplifiers. The first one, hopefully it's quantum limited. And then you can have a second amplifier, which is not necessarily quantum limited. And still, as I will show you next, you can get a full quantum limit for the whole measurement chain. And the idea is the following. This is something you can find in any good electronics textbooks. If you chain amplifiers, you can show easily that the noise of the total system, the system noise temperature, is the noise of the first amplifier, so this little guy here, plus the noise of the second amplifier divided by the gain of the first one. And if you have more amplifiers, you can extend this formula, obviously. And this is a very simple formula, but still it gives you two main constraints. First, you want the first amplifier to be as low noise as possible. If it can be standard, if it can be at the standard quantum limit, that's of course the best case. But that's not the only requirement. You also want it to be large gain, because if the gain of the first amplifier is not large enough, you will be spoiled by the gain of the next and the next amplifier. So this gives you this limit. You need your amplifier to show a gain which is at least 20 dB. And here I am plotting the full system noise temperature versus the gain of this red of this first amplifier. And you see that if its gain is too low, you have something which is very far from quantum limit. And if as soon as you reach a gain which is around 20 dB, you see that your full system is almost quantum limited. Okay, so that was a just simple way to introduce you these two targets: standard quantum limit for the noise, 20 dB for the gain. Okay. So far, I just told you about the concept. There was no recipe. There was no explanation on how to build such a quantum limited amplifier. So now let me try and walk you through the physics of quantum limited amplifier and how to build one. So to do so, we use what's called parametric amplifier. A parametric amplifier is a type of parametric oscillator, and in our case, an electrical one. So let me first start with a mechanical parametric oscillator, which is extremely well known. It's called a swing. All of us have ever experienced that. And the idea is the following: you have an oscillator, which is the swing, and if, excuse me, the kid changes the moment of inertia of the swing at twice the frequency compared to the oscillating frequency of the swing, the swing amplitude will increase with time, right? So if you pump, if you wish, at the right frequency and the right quantity, you can get amplification, and we have all experienced that once in the kindergarten. Of course, as I said, we are dealing with electrical parametric amplifier. So in this case, what we change is not the moment of inertia, it's the impedance of the circuit. So if you can build an oscillator, for example, an LC oscillator like this one, but we can vary, let's say, the inductance of the oscillator and vary the inductance at twice the frequency, the resonant frequency of this oscillator, we will get some amplification, we'll get some gain. And nature has been kind with us because there exists a component which allows you to do that exactly as I said, and importantly, without any dissipation. This component, I guess you all heard about it, and it's called, a Josephson junction. So this is just an SEM image of a Josephson junction that you can view as a parallel tunable LC oscillator. Okay, so this is the heart. This is really the engine of our parametric amplifiers. So this was a classical description. If you're more into quantum optics, you can now use this equivalent description I will talk about. They will give you the same result at the end. One is classical, one is quantum. It's really up to you. So now this is the quantum description of a parametric amplifier. You can view such devices as multi-level systems. The idea is that you will use a pump to excite this multi-level system. And then whenever a signal photon shows up, there will be some stimulated emission. So the system will emit two photons, will decay and emit one photon at the signal frequency, and another photon, which is called idler or sometimes complementary photon, so that at the end of the day, you conserve energy, right? At the input, you have two pump photons. At the output, you have one signal and one idler photon, so you fulfill energy conservation. But now, what is interesting is that you have gain. Indeed, if you focus only on signal photons, you see that at the output, you have two signal photons, while at the input, you have one signal photon. So you see, it's a very simple, probably too simplistic amplifier, but it shows gain. You have gain of 2. As I said, it's probably useless, but if you can boost this gain, it's actually a very, very good starting point. So now the question is how to boost this gain. And the answer is probably obvious. The first thing you might think about is to increase the interaction time between this nonlinear medium, between this parametric amplifier and the photons. And to increase interaction time, you can just put that into a cavity. And then the cavity, the interaction time is just given by the cavity frequency and its quality factor. So if you have a very large quality factor, you will have a very long interaction time, and you can have, you can send one photon in, it will be amplified to 2 photons, then to 4 photons, and etc., etc. And if the interaction time is long enough before these photons escape, then you can have large gain and you can reach 20 dB. So this is one first scheme: a nonlinear medium, a parametric amplifier into a cavity. Obviously, here there is a limitation, an inherent limitation, which is the narrow band of this device, because it's a cavity. So there will be some line width, there will be some reduced bandwidth. So if you want to escape this, you might want to find another strategy. And this other strategy is to distribute your dissipationless nonlinear medium, is to distribute your Josephson junctions. And if you do so, the interaction time is now proportional to the length of the medium divided by the wave velocity. So if you can make your amplifier very long, and if you can make your light very slow, you will have a very large interaction time. And exactly as I've shown you before, you can have amplification. So one way of thinking that is that instead of having one cavity with many with photons bouncing back and forth many times, it's more like having photons amplifying step by step along the medium. And this is what I depicted here. You see that at the input, you have almost no signal and no idler. and a very strong pump, and then gradually along the device, energy is transferred from the pump to signal enabler. And the obvious advantage here is that there is no cavity, so you can have, in principle, an infinite bandwidth. Of course, it's never the case. You have to fulfill other criteria, but you see that you can then escape the bandwidth limitation. So such concept was first explored in optics. People used nonlinear crystal, such as this one. And then the idea is that you have wave, an electromagnetic wave, an electrical wave in this case, described as a plane wave, which propagates into your medium. And now in this crystal, you can show that the polarization is proportional to E, but it's also proportional to E squared with the coefficient chi2 to E to the 3 with the coefficient chi3. So this chi2, chi3, chi4, chi, etc. are really the nonlinear coefficient of your device. And interestingly, you can build exactly the same kind of, I would say, concept, exactly the same kind of formalism, but for an electrical device. This device is not made of nonlinear crystal, obviously, but as you can guess, it is made of Josephson junctions. And as I said earlier, this idea was pioneered by Irfan and his group, by Chris and Kevin 5 or 6 years ago. So the idea is the same. You have an input pump, an input signal. They will travel along the device at the same time. And if you if you fab your device and if you design it properly, at the end of the day, you will have some energy transfer from the pump to the signal and to the idler. And now you can also write some equation. Now you are not dealing with the electrical field, you're dealing with the phase, which is nothing but the integral of the voltage. Again, this phase, you treat it as a plane wave. And now you can show that it's not the polarization, which is proportional to the electric field, it is the current, which is proportional to the phase. But in a very similar fashion than for crystal, this current is also proportional to the phase square with a coefficient which is basically chi2, or to the phi to the cube with a coefficient which is nothing but chi3 for electrical circuits. All right, so this is the electrical circuit version. This is the electrical circuit translation of what's been done in optics for many years. Okay, so I am almost done with my introduction. Are there any questions in the audience? Okay, so let's go. Let's continue. Okay, so now I will really show you some devices. I will treat this question about phase matching, and I will explain you what is phase matching. So first, let's start with a real device. I am an experimentalist. So this is the kind of device we fabricate in my lab. You have a long array of Josephson junction, or of squid in this case. We speak about 2000 unit cells. So to do that, you need a pretty good e-beam writer, but nowadays this is quite available in many labs. And then you want to have some ground plane to get some ground capacitance, which is large enough. So everything is, I mean, basically the idea is to tailor the impedance. So you have some Josephson junction transmission line, which is 50 ohm, because of course, if it's not 50 ohm, the thing is not matched to your measurement circuits, and you can do very little with that. Excuse me. So this is a device. This is an optical micrograph. You see that you have all the small junctions there. Here you have some taper for CPW, and then you have a CPW to microstrip transmission. If you want to discuss the fab, we can go more into the details later. So now, if you just measure the gain of this device, I will not, excuse me, explain you. I will try not to die tonight. That would be a shame. So let's say that you now measure the gain of this device. So the blue curve is the traveling wave parametric amplifier. And the green curve is another type of device, the resonant one I spoke about. I did not describe this device, but just trust me, this is just the resonant version I described before. And at first sight, you see that there is already a very large difference between the resonant amplifier and the traveling wave one. And it's kind of obvious that the bandwidth here is much larger than the bandwidth there. So you might say, hooray, that's great. I'm done. I have my nice amplifier. I can go and measure my qubits. But if you look a bit more carefully, you see that there is a problem here. The gain here is very much limited. And even though you have your 20 dB gain as requested for the resonant amplifier, you're very far from that for the traveling wave amplifier. And the reason is quite simple. As I told you before, you need to fulfill energy conservation whenever you have parametric amplification. In other words, you want signal frequency plus idle frequency to be equal to twice the pump frequency. And this is always true for any parametric process. The problem is that whenever you transition from a resonator, a resonance structure, to a traveling wave structure, you have a problem now with the K vector only. Because if you have a resonance structure, it's like you have 0D, so there is no K vector, you don't even need to care about what is a K vector. If now you have a 1D system, a traveling wave system, K vector is very well defined and you have to conserve it as well. So this is what people call momentum conservation or phase matching, if you want. And similarly to this, you want to make sure that delta K, which is equal to 2kp minus ks minus ki is equal to 0. And if you don't do anything, you don't have this. And it's not a priori true. So this is why the gain of the amplifier I've shown you before is very much limited to 10 dB. Here, I decided to put a bit of equation to understand what's going on. And the idea is quite simple. So here you have the wave equation. So this is the linear part. So this is what you have for a standard plane wave. And you see that you already have some problem here. Usually you have some dispersion. The dispersion relation of your waveguide, of your transmission line is not, strictly speaking, linear. By this, I mean that omega, the frequency, is not directly proportional to k. You might have some bending. So already, if you have a nonlinear dispersion relation, you see that delta k is not 0. So this term, basically here, is already troubling you. But there is more. As I said, you need some nonlinearity to get some gain. The problem is that this nonlinearity, which is your friend for the gain, is also a foe for phase matching, because it will introduce what people call cross-phase and cell-phase modulation. And at the end of the day, your delta K is also non-zero because of this nonlinear term. And you can show that this nonlinear phase mismatch is directly proportional to the pump power. So at the end of the day, you have two causes for your phase mismatch, one which is coming from the dispersion relation and one which is coming from the nonlinearity of the device. And if you combine these two, delta K together, you can show that now the power gain is proportional. I mean, it's not proportional, but depends on this delta K. And it's actually a very strong dependence. And if your delta K is not 0, you see that your gain will drop very quickly. So basically, we'll have a linear part here and also an imaginary part here, which will reduce your gain, and also your G here, which is the one you find in this exponential function here, is also reduced by delta K squared by 4. So if delta K is non-zero, your gains drop very, very quickly. So the question is how to phase match your device, because you see, you need to deal with the dispersion relation of your device, you need to deal with its nonlinearity, and how to deal with that, that was really the breakthrough I think Irfan and his team realized in 2015 after a proposal of Kevin in 2014. But before I get there, let me explain you what people in optics do. So in optics, they have crystals. So they can make crystal, they can stack them, they can have different type of crystals, they can also have take advantage of different angles. So this is what's called angle phase matching. Here it's quasi-phase matching. So basically they are taking crystals with different nonlinearities. So they stack them. So they somehow flip back and forth the sign of the nonlinearity. So there are various tricks. But I think that with circuits, we have something which is actually cooler, which is actually more powerful, because now we can really engineer our material, our metamaterial at scales which are much, much smaller than the wavelength. So as I said, it's relatively easy to have thousands of cells. The size of a given cell is, I don't know, between 1 and 10 micron, while the wavelengths will be almost millimeters. So you see that you can put many, many cells per wavelength, so you can really play with your material at sub-wavelengths. And it gives us very much and very important flexibility. Okay, so as I said, the first trick, which was used by Irfan and Chris in 2015, is this one. So their idea was to use a technique which is called resonance-based matching. The idea is that every other cell you add an LC circuit, an LC resonator, so you will give a little kick to the phase, and you will somehow backbend your dispersion relation and get rid of this delta K caused by both the dispersion relation and the nonlinearity. And they did that very nicely, and this is why they obtained this very nice curve, which is super famous. So you see that now you can have large gain, more than 20 dB over a very large bandwidth. So more recently, we used a different technique, which is, I would say, probably simpler. Instead of adding resonators, which might be difficult from a far point of view, we used a much simpler trick, which is to, have periodic modulation of the size of the Josephson junction. So it's similar, this device is similar to the one I've shown you before, but now you see that the size of the junction is varied periodically. And here you have a true optical micrograph of the junction. And if you do so, if you remember your solid state class, you will open a gap. This is the Bloch function, the Bloch theorem. If you have some special periodic modulation, it will create a gap in the dispersion relation, Bloch wave functions. And this is actually what we did and what we used. So if you plot wave vector versus frequency, you see that instead of having a linear dispersion relation here, you have some curvature and some gap in the middle. And so now you can tune this curvature, so this delta K here, so that it compensates exactly the nonlinear part, the KR part, so that at the end of the day, the total delta K, so delta K naught plus delta K KR, goes to 0. And then using this gap, you can get your phase matching condition. So doing so, these are the results we obtain. So this is the blue curve. So this is a little podium that my students like to show. So I kept it on my slide. So first you have the resonant parametric amplifier. Then you have the dispersionless, the bare tuba in black. And you see that if you do some dispersion engineering, you have a much higher gain. You reach the 20 dB on, again, very large bandwidth. So you see how you can go from resonant to traveling wave to phase match traveling wave. And every time you gain in bandwidth. But then more recently, we thought, okay, can we play a bit with the physics, and more importantly, can we do better? So as I told you before, to phase match, what Irfan and his team did, or what we did, was to do some kind of band engineering. So we changed this part of the delta K. We played with the bands. Irfan and Chris added some resonators. So of course, there are different techniques, but they are always acting on this part of the phase matching. And we thought, okay, can we do something to engineer the nonlinearity? Can we forget and try not to cure this guy, but still get some phase matching. And if you don't do anything to this guy, then of course you need to do something to this care part. So the idea is the following. Instead of using a squid or a Josephson junction, you use another beast, another mollusk, which is called the snail, for superconducting nonlinear asymmetric inductive elements. So it's a small Josephson junction shunted by 3 large Josephson junctions. It looks quite similar to a flux qubit or to an RF squid. If there are specialists in the audience, I'm happy to discuss the details, the slight discrepancies, but you can somehow view that as a kind of RF squid. But why is it so interesting? And the answer is pretty simple. It is interesting because now you have all the terms in the current phase relation. So you have a phi square, you have a phi cube, but more importantly, you can change the sign of this gamma. You can change the sign. This gamma is like the Kerr coefficient. So you can make it positive or negative depending on the flux that is trading this loop. So if I write the wave equation similar to the one I wrote before, you have again this linear part I described. You have now this chi2, if you want, part, and you have this chi3 part if I use the optics naming. And as I promised, if I now change the flux training each of these snails, I can change the sign and the value of beta and gamma. And we decided that we wanted to operate our device. I mean, we built it to be operated exactly at this flux. So at flux equal 1/2, you see that beta equals 0. So this term is 0. And now you have a negative gamma. You have a negative Kerr, if you wish. And now it's kind of interesting because if you look at the delta K, so the delta K naught is still positive as before, but now the delta K Kerr is negative, and you can actually tune it so they perfectly compensate. So this is the trick we used. So instead of working on that, we work on this guy, and this gives us actually a very strong asset, I would say. It gives us a very nice feature, is that we don't have any more a gap. We don't have any more a dispersive feature in the dispersion relation. So we can pop anywhere, basically, and we get some large gain. So this is the device. So specialists will notice that these snails are alternated. The idea is to really kill completely the beta, the chi2. And we use our favorite fab technique, which is the sandwich of dielectric and the top ground. And here you have an SEM picture of our snails. So here you have the small junction, and here you have the 3 large junctions. And now these are the results. Again, I compiled our data from the last 3 to 4 years. So this snail traveling wave parametric amplifier is the green curve. First, you see that the band is quite larger. The bandwidth of the amplifier is quite larger. Also, as I told you, there is no notch. There is no forbidden band. You have amplification everywhere. And also, you have way less ripples for the snail. And we understand it because since there is no dispersive features in the transmission line, the impedance can be kept to 50 ohm everywhere in the device. So this is why we have way less ripples compared to the previous implementation. Okay, so I think in the 5 to 10 minutes, 5 to 10 coming minutes, I will switch gears and speak a bit more about quantum optics and more specific.
Take 10 minutes.
10 minutes, I'm good.
Don't hurry too much. Okay,
great. I wasn't sure about the timing. Good, 10 minutes. That should do it. Thanks. So yeah, so I've shown you that these devices, this Josephson metamaterial can give us very, very nice amplifiers. But now let's play with them and use them as would say, generators of squeezed or of quantum radiation. So as I said, it's not only an amplifier, it can also be used for microwave, quantum microwave photonics. So if you want to use it as an amplifier in the pump and a signal, then you amplify your signal at the output. If now you just pump it and you don't send anything in, just vacuum noise, you can get some squeeze state, some vacuum squeeze state at the output. So this is something which has been heavily studied, largely studied in resonant Josephson parametric amplifiers. First demonstration in 2008. Then people used also it for two-mode squeezing, storage and entanglement. Also, squeezing was used to improve qubit state measurements, and more recently, even to enhance dark matter search. So squeezing is really, in microwave squeezing is really a very active field. But so far, it was never, to the best of my knowledge, observed in a TUPA. It was only restricted to resonant JPA. And the obvious question is, can we generate squeezing in TUPAs? And is it cool? Is it interesting? Is it useful? So there are pros. Of course, if you have a TUPA, your squeezing will be broadband. Obviously, it's the TUPA amplification band is much larger, so the squeezing nature, the squeezing will also be much more broadband. That's for many applications, that's very, very important. Also, as I showed you, you can easily customize and flux tune the nonlinearities, so you could have various types of squeezing at will with the same device. You can reprogram it in situ, you don't have to build another device. So these are the pros. But there are two limitations. This is something I did not mention so far. Usually, TUPAs, since they are long devices, they suffer from loss. So overcoming this loss is really a challenge. And also, since now you have something which is much more broadband, you might have spurious nonlinear processes. So you also have to understand them and mitigate them to get proper squeezing. And this is what
having bandwidth can have its benefits, but the thing with the TUPA is that it has too much bandwidth. It has a lot more than what you would ever need.
You know, not everybody would agree with that. Sometimes people are asking even for more bandwidth, and it depends on,
it depends on the application.
It depends on the application, yeah. But if you think about, let's say, communication schemes, if you want to have very broad, very large entanglement between many frequencies, if you want to build cluster states or things like that, having large bandwidth means that you have something which is heavily multimode, and people are even thinking about this as an alternative for quantum computation. So more bandwidth, also more qubits if you want in this context. Okay, so this is the device we used. Long story short, we used a much shorter device. Now it's 250 cells. This was our trick to reduce loss. Of course, loss are directly proportional to length. So if your device is shorter, you have less loss. As simple as that. We operate this device in a 4-wave mixing fashion. So you destruct, as I told you before, 2 pump photons, and you create one signal and one idle photon. Now, if I want to rephrase maybe this 4-wave mixing Hamiltonian and speak more about a squeezing operator, it's pretty straightforward. I can write a squeezing operator this way, and the squeezing parameter is this psi here, which is a complex number. And just for your information, there is a link between R, this squeezing parameter, and the gain of the TUPA. What is neat is that you can apply this squeezing operator to the vacuum. So you have vacuum for the signal, vacuum for the idler, and if you apply the squeezing operator, you will end up with this entangled state. I wrote it in the Fock space here for your information. So actually, you can think about your TUPA as a device which will apply this transformation to your input vacuum. Okay, so this is our setup. We have a pump to obviously pump the device, and there is nothing else than the pump. Then we have some amplification chain. One key device in this experiment is not only the 2-pi itself, it's also this RF soft module we program to get broadband width and a fast digital treatment using the FPGA. That might be interesting for people in the audience. And the idea is that then we can repeat an experiment very, very fast, which is to measure INQ XNP of the signal, INQ or XNP of the idler, so in phase and out of phase quadrature for signal and idler. And we can repeat that and take histograms of this. And the idea is that now what I call signal is something which is at frequency lower than the pump, and what I call signal is a frequency which is higher than the pump. And the 4-wave mixing will mix idler and signal thanks to the pump. So this is the scheme. These are raw data. So these are phase space histogram distribution. I took these 6 histograms. So you have PS and XS here. You have PI and XI, so I for idler, S for signal, and you can look at all the various combination. And already on this raw data, you can see some kind of orientation. You see that here, the phase space distribution is quite round, while here there is already a preferred axis. You need, of course, to go a bit further if you want to claim some squeezing. So you want to reconstruct what is called the covariance matrix. For qubit people, it's like tomography for continuous variable, and this Manhattan plot, this kind of bar plot is exactly what you would have, or very similar to what you would have for 2-qubit density matrix. And so here it's not a qubit state; it's more like quadratures of 2 different modes. And so this is the covariance matrix we reconstructed from this raw data. And what is interesting is that you have very strong, very large off-diagonal elements. So for people who are used to tomography with qubit, you can already tell that, okay, there is probably some cool correlation there. Now you want to quantify this correlation, of course, and see if there is some entanglement. Is there any question in the audience? Maybe not. Okay. So one way to quantify this entanglement is to calculate something which is called the logarithmic negativity. I will not give you the formula because it's a bit cumbersome, but the idea is to quantify the relative height between the diagonal elements and the off-diagonal elements. You can also define what is called a squeezing collective quadrature, and which is defined as this, and calculate this amount of squeezing. These are two equivalent metrics. And if you do so, this is what we obtain. So here you have this collective quadratures, X plus or P plus, as a function of the pump phase. And you see that whenever you have a given pump phase, you have a very large,
I am not super familiar with that entanglement measure. In your plot, what values will correspond to no entanglement and to full entanglement? Is it 0 no entanglement?
Yeah, I was about to go there. Yeah, so if you look at this plot, for example, if you're above 0.5, there is no entanglement. Everything is classical. You can think about this 0.5 as the vacuum fluctuations. But now for a given pump phase, you see that for this quadrature, you are much lower than 0.5. You are much lower than vacuum fluctuations. So you have squeezing and then entanglement. Okay. So or you can plot this logarithmic negativity here. And in this case, this logarithmic negativity being larger than 0 tells you that you have some entanglement.
Okay, so for that one, 0 is no entanglement, and anything above is entanglement.
Exactly. And for this one and this one, it's the other way around. You need to be below 0.5.
And for that lower plot, for a lower plot, 1 would be maximal entanglement.
I mean, in principle, this can go to infinity. There is no
okay. So it depends on the measure.
It depends. Yeah, exactly. So you can go in principle as high as possible, and this gives you, if you want, how many bits per second you can produce. So you want this to be as large as possible. But 0.5 is quite similar to what you would have in a resonant parametric amplifier, in a standard JPA, if you wish.
Okay.
But sure. I think the most important thing is really this plot, because now I promised you broadband, so we wanted to test this broadbandness, and we measure these two metrics, so the squeezing or equivalently the logarithmic negativity versus the tuning between signal and idler, and you see that we can generate squeezing between very far detuned signal and idler. Here it's 200 megahertz on both sides. And actually, we were limited by the bandwidth of our electronics. Probably the device can give us even more, even more bandwidth. It's just that at one point we cannot measure it because the analog bandwidth of our electronics is not large enough. Okay, so I guess it's probably now time for me to conclude. So today I told you about Josephson metamaterial used as Josephson parametric amplifiers or traveling wave parametric amplifiers. I discussed how to phase match these devices to get the largest possible gains. We use two different techniques, either one with a gap, some bond engineering, some photonic crystal approach, or we directly act on the nonlinearity itself. And in the last part of my talk, I discussed our first observation of two-mode squeezing in a tuba. Also, if you are interested, we recently wrote a small perspective about what we could do in the future with such devices. Okay, I would like now to thank you again, and thanks all the team who helped us with these experiments. Thank you.
Okay, thank you. Let's clap virtually for Nicolas. And let's see, is there any questions or comments?
I have a question. Thank you for the nice talk. So I have a question about inhomogeneity. It seems that so there is both the junction and you also have the flux to be put onto your Snail device. So how much inhomogeneity caused a problem to this device, and how did you fix it?
So that's a very good question. So to tell you the whole story, we could. So first, there were two questions in your question. Inhomogeneity regarding the junctions. So we tested that. Basically, we fabricated many junctions, many numerically identical junctions on a wafer. We tested that on 2-inch wafer scale. And for such large junctions, we have homogeneity or inhomogeneity, if you wish, of 3%. So if we measure the normal self-resistance, we have 3% on a wafer, on a 2-inch wafer. So this is, if you put numbers much lower than what you need for such device. The thing which worried us much more is the flux, magnetic flux homogeneity. And at one point, we did some calculation, some estimation to make sure that everything was homogeneous enough. And to tell you the whole story, we make a Helmholtz coil, so two coils like that to get the best homogeneity possible. And then at the end of the day, we went to only one single coil, much smaller, and the device worked the same. So I think at the end of the day, flux homogeneity is not such a big issue, and the physics behind, the rationality behind is that you have so many cells that if you have some disorder, it will basically average out. So that's my understanding.
But because it's 1D, like usually disorder is really bad in 1D.
You have to calculate the localization lengths if you want to be more specific. But what you can show, if you want more theoretically, you can show that the device is much shorter. So that's no big deal.
Okay. Thank you very much.
You need basically to give you a number. If you have disorder which is more than 20%, you start to feel it. We are almost an order of magnitude lower.
Okay.
Any other questions?
I got a question. So since you are using flux to control the device, and I imagine that it also opens up a channel for noise to get into to be also parametrically mixed in with the signal. Do you see any? Do you see like what the kind of noise gets mixed into the signal?
So do you have in mind external noise for the squeeze? You
yeah,
speak
if
about
you
the
have
squeezing
like
experiment.
For the amplification.
For the amplification. I mean, we use a standard filtering approach. I mean, of course, we should discuss the kind of noise level you have in mind, but to tell you the whole story, there is no magic, no trick. We use attenuators on the input line, KNL filters. We have a bunch of EcoSort filters as well on both input and output line, I think. But there is we don't see anything really more stringent, I would say, than whenever we do standard qubit experiments.
Yeah.
Does it answer the question, or
yeah, just because now you have so many like squid or snail loops on it, so I will imagine that any noise that goes into your flux line get also mixed in with the signal and also potentially amplified if that really works. And,
okay,
yeah.
I see. Okay, you had in mind noise. Okay, noise on the flux line. Okay, it's okay. I get it. Sorry. So two things. First, we use an external coil, a large coil. So our flux lines are super slow. So it means that the inductance of this coil is extremely large. So it gives us some very low pass filter. So the coil itself, if you want, is a filter. First. Second. You see, we have this kind of gradiometric design as well. So by flipping cells, it gives us also some kind of immunity against external flux noise. But to tell you also maybe detail to feel how sensitive or not is the device, we don't use any mu metal shield, and still it works very nicely and it's stable for days.
Okay, that's pretty impressive. Thanks. That's
sure.
The last one. It's quite concrete.
Yeah. I guess that I should have said that straight away.
Yeah.
Okay. We're a little bit over, but if there's one more question, is there any other question?
Hey, I have one more question. Nico, thanks. A great talk. For the broadband squeezing, seemed like almost that the squeezing quality of the entanglement was improving with the tuning between the idle and the signal.
Oh, yeah. And here you mean?
Yeah. Is that kind of surprising? And what are really the limits on how broadband this can be?
Honestly, yeah, I agree. There is some trend here. So I'm not sure I would, given the error bars, I would not conclude anything on this trend. Now, of course, if your detuning is getting, I mean, if your delta is getting smaller and smaller, then you might face some aliasing or some, purely numerical problem. So here, I can imagine that if we bring signal and idler very nearby, because of our detection scheme, that might be a problem. Now, the fact that this is kind of getting higher there, I don't think it's just that the error bars are this way. Now, what about the limit? I think the limit is just the bandwidth of the amplifier. So in principle, if our RF sock, let's put it this way, if the analog front end of our RF sock was even broader band, we could go to gigahertz here. We are really limited by the detection electronics, if you wish. So in principle, in theory, the only limit is the one of the two.
Very interesting. Thank you.
Sure.
Okay. Yeah. Thanks again, Nicolas. It was a very good talk. So let's thank our speaker again.
Thank you very much.
Thank you, everyone. Have a great Thanksgiving.
Thank you. And see you soon, maybe at the March meeting.
Yep, hopefully.
Yeah, hopefully. Bye-bye. Have a good day.
Bye.